Hello, this is the first in a short series of lessons about how to find the shortest path from A to B in a map or other structure. In this first session, I'll introduce the data structure that we will use, which is called the graph data structure. In this lesson, you'll find out what the graph data structure is, look at the different types of graph that are available, and think about how we can make use of this data structure to solve real-life problems. A graph looks like this. The picture you can see on the screen at the moment is a graph. It's a data type that's made of nodes called vertices, and they're joined by links that are called edges. So in some ways it's quite similar to other data types that we've looked at. But unlike a tree, for example, a graph doesn't have a regular structure. The nodes can be connected in any way and they don't form a neat shape. Each graph has a different shape. Most graphs that you will look at will look like this example. This is called a weighted graph. The weights are the numbers that are attached to the edges. They're always numerical values. In this example, they're integers. They don't have to be integers, but they are always number values. The weights represent the amount of effort or time or distance between any of the nodes. For example, if this was a map, a conventional map of a place, the numbers might represent the number of miles between the different places, but it could be any recognition of effort. It's worth noting that a graph data structure doesn't have to be drawn to scale. So you'll see that the edge that connects A to F has a weight of 14, and the edge that connects A to C has a weight of 9. They're drawn at more or less the same length on this picture, so it's not to scale. But the numbers represent how much work it takes to get from one place to another. So to get from B to D is quite a lot of effort. The number is 15. To get from F to C is not very much effort. The number is 2. So now you know what a weighted graph looks like. Some graphs have arrowheads written on the lines, and these are called directed graphs. So in a directed graph, the connections only work one way. So in this graph, you can get from F to C, but you can't get from C to F. In this graph, you can't get to E at all. There are no routes going to E, only going away, whereas there are routes going to and from node A. So the arrows show you the direction you can go. So if you were shown a graph like this in the exam and asked to describe what is this data structure, you'd say this is a weighted, directed graph. You know it's weighted because there are numbers next to the edges, and you know it's directed because there are arrowheads drawn on the lines. The examples we'll look at in this presentation will use undirected graphs. That is graphs where there aren't any arrowheads and you can go either way down any of the lines. But in the exam you might see either. So when we draw a graph, the vertices are always shown as circles, sometimes points, and each vertex has a name. I tend to use letters, but they can be full words, and the name is typically put inside the circle or sometimes written next to the circle. The edges are lines and the weights are drawn next to the lines. You won't be expected to draw a graph, but you should be able to understand a drawing of a graph. So what's the point of the weights? Well, a graph is typically used to store information about whether there is a path between two states, and the value represents how much work or effort it is to get between those two states. With this information, we can then work out what is the easiest way to get from one position to another. They could be literal physical positions, like those nodes could represent train stations or airports, and we're literally traveling between them. Or they could represent states, let's say, of a chemical reaction, and the lines could represent that we can turn a molecule into another molecule in a chemical reaction. So this sort of data structure is used in your sat nav in your car to literally find the shortest route. The algorithm used by sat nav is somewhat more complicated because they take into account other factors, but the shortest route on a sat nav, or it might be used by the electricity supply companies to route power through the wires of the electricity network, because obviously the more wire that electricity is pushed through, it loses some power through however long the wire is. So they're trying to minimize the use of the network. Or the college network itself, we could use an algorithm like this to route signals back to the server through the most efficient route. Or, as I say, they could be abstract. It could be an abstract representation of a chemical process or some other sort of process in industry, and the numbers represent how much energy or how much effort or time it takes to transform different products into each other. So when we talk about shortest path, it might literally be the shortest path. That is, if they were, let's say, train stations and the numbers represented the miles between the stations, we could use the graph to find the shortest route in miles, let's say to get from Nuneaton to London. But as the numbers can stand for other values, the shortest path doesn't have to be literally a path, and shortest doesn't literally have to mean shortest in miles. So your sat nav probably uses the minutes of travel rather than the miles between two places. So it might take you on a longer route, let's say on a motorway, because on average you can drive faster and you'll get to your destination more quickly rather than just finding the shortest distance in miles. Or you might have an AI that's planning your journeys around, let's say if you were a businessman who had to travel around the world, then your AI might consider the cost of the different plane tickets in order to minimize the expense of getting to your different meetings. The college network algorithm might look at the bandwidth that's available and look to send the signals through the most high capacity cabling. Or in a chemical formula, if you're trying to turn one chemical state into another, you might think about what energy needs to be put into the reaction so that you can produce the outcomes that you want the most with least expense on energy. But these are just examples. However, I'm now going to just talk about distances and numbers, and just be aware that these numbers can represent all kinds of different things. But an easy way to imagine it is to think about we've got a map and we're looking for the shortest route through the map. And there are two algorithms that we can use to work out the shortest path from A to B. And we're going to look at those over the next 2 weeks, and you're going to learn how to do these algorithms. The two algorithms are called Dijkstra. That's how that first word is pronounced, Dijkstra, and A star. Dijkstra is a way of working out the shortest path through mathematical formulas, And A-star is more or less the same as Dijkstra, but there's an extra heuristic that helps us to get to the right answer more quickly. Can you remember what a heuristic is? If you can't, that's your task at the end of this lesson. Go and read up about what a heuristic is and think about how a heuristic could help to make a more efficient way of getting your way through a map to the correct destination. Okay, so in the next presentation we'll look at Dijkstra's algorithm and you'll learn how to do the Dijkstra algorithm on paper. See you soon.